I am in the directory where the Tiago has been installed, so source, the bell, setup bash to make sure that everything is set up properly. We fire Gazebo from the tutorials. We are in the motion command tutorial. What is the message that gets sent to make the robot move? We're going to go to another window. We have the move command from the previous version with the turtle bot. Edit the forwards motion and replace the topic that is for the turtle bot and place the topic for the Tiago. Test that we can make the robot go forwards. So this is a repetition of seminar 3 for the Tiago. From previous labs, run Ros core, run the turtlebot simulator. We could run this machine. So the first part of lab 3 is to produce this same behavior in another robot. What we're going to do is copy that machine. We're going to create the package. I'm going to go into this new machine, create a directory machine. We're going to run 2 instances of the editor. The first one, open the old machine. Runs blind turtlebot machine. This is its initial state. Open another instance of this editor. While new, this one is going to go into the workspace source into the package we just created. The name we're going to give it is the same name in our package. So this is the initial state, exactly the same. Save the state. I have the state to go straight. Add a state. Save it. Turn right. Add a state. Copy it. Save. And doesn't have anything. Add a state. And let's go to our initial state. Look at the transitions that we have. That the target is straight with expression after milliseconds, and that's the only transition that we have. Add a transition from initial to the target straight. Okay. After milliseconds, 1000, which is equivalent to. Okay, state. Save the state. Now let's go to straight. Now look at the transitions. It has two transitions. One is to turn right and one is to end. Straight. Add a transition to turn right. After. Save the state. I'm going to add a transition to end. Not Ros. Okay. Save the state. Turn right. The state turn right has some behavior. We need to add transitions. Again, the transitions that we have here are two. Back to straight and to end with not Ros. Okay. Add. We add to straight. After milliseconds 1,000. It seems we have everything cloned about our machine. So we're going to make sure that this machine works. And I have to compile it. So let's copy from our Ros blind turtle bot machine or script. Remember the script machine setup will do the corresponding split. Give us a suggested file. We look at the dependencies as we created the package. Incorporate those into the suggested. Copy the suggested into the CMake list. We're going to go to a place where we can compile in. Now we do have an error. This error is due that we haven't really copied everything about a machine. There is variables. The error that we're getting is not because of the variables, but it's because of the include files. Save. Because I changed the machine, although I didn't change it structurally, I'm going to have to do the split again. I can try to compile, and now we're going to get a different error. We don't have the corresponding variables. Precisely, this is the one that the compiling was objecting here, remember? Because the machine changed, we split again, and we try to compile again. And we're going to try to run you're going to need to run ROScore. You're going to need to run the little turtle, and then this copy of the machine does the same thing as before. Remember here in these tutorials, remember this is the topic. Go to the state initial, change the topic for Tiago. This is now the new topic. Save the state. Because we modified the machine, we do a machine setup. We need to compile it. Copy the live Ros blind PR2 to Ros blind PR2 Linux Ros blind PR2. So run Ros core. Let's look at Ros topic list just to check that we're publishing in the new topic. If we run the machine, we're publishing in that topic. Let's check echo. So we see that we're going straight and back. Stop the machine. Stop Ros core. So we launch Tiago in an environment. Prepare to run the machine. Now the robot makes a bit of a different movement because it moves straight and turns. So it's not necessarily doing the triangles that we saw before because its units are different, but certainly the machine is doing the behavior of going straight for the corresponding equivalent of a second in the simulation and then turning right for a second. I'm going to try to demonstrate the program Ros switch. In this case, is being tailored for the Tiago robot. So this is going to be a node that works as a subsumption switch. Run an environment from the tutorials of the Tiago. I already have these compiled, so I assume you're already familiar with how to compile. So here is the switch node, and at the moment it's posting stop. We're gonna also provide you with Ros switch commands. So if you want to look at one of them, right? So here are some of them. Lab3, no command at priority 1. It's just publishing. Let's have a look at it. You can see that the node is publishing stop, and at the moment the robot is not moving. Among the commands that I have, one of them is to move forwards at priority 1. Let's look at that command. You can see that it's just publishing in the corresponding topic at priority 1 a command called 3. This gets captured by the subsumption switch, which you can see here is posting ahead, and the robot is moving forwards. Even if I stop, the robot continues to move it forward because in the switch, we haven't said anything different. If I say something at priority 2, the robot starts to spin to the right because the switch is in a state, it has received these, and now it has a command with highest priority. Even if I say Control C, the subsumption switch keeps continuing with that message. Interesting thing is that if I say no command at priority 2, this will remove the command at priority 2 but we'll leave the command at priority 1, which, if you remember, is to move forwards. The status of the switch is that we're moving ahead. Now, if I say no command at priority 1, I remove that, and because there's no command at priority 1, then actually the robot doesn't do anything. I'm going to show you now a wrapper for sensors. It's called Tiago Laser Scan to Total Sonar because besides being a wrapper for the laser scan of the Tiago, it's also going to try to produce a service similar to the original sonar sensors of Toto. Download this package and compile it in your workspace. Run the robot in an environment. Run the keys. These programs record the laser scan that you see here and try to convert that into regions and wedges for the sonar sensor, whether there's an obstacle or not. So apparently here there's not an obstacle, and also we can get information about it. Is something that doesn't require any arguments. If we actually call, here you get the values of the sonar sensors. Basically nothing is, there seems to be something about a meter away. So let's try to move the robot to a certain position. In the screen that we're reporting the values, you get an idea of what is happening. This is the log of the wrapper. You can start to see here that the values get very close to 80 centimeters. If we actually make a call now, this will be the equivalent of what a behavior, a logically equal finite stage move will do. Sonar 2 and sonar 3, which are at the front, are about 78 and 81 centimeters, very close to the wall. Let's get even closer. Let's query our sensor. We are 55 centimeters. If you want to get a bit curious and very close to the wall, 38 centimeters in the front sensors. If we spin the robot around, not only the ones at the front, but others start to have, like sonar 1 says, let's spin it around a bit more. Now even sonar 0 show you the stroll behavior for the Tiago. This stroll behavior is provided to you. We will highlight here how do you create the package. At the moment in this machine I have creating it under my downloads. So to show you where this is, I'm gonna open the machine. At the moment here is in my downloads, my calculate workspace, and my source. You should have created using this instruction that you see here, and I highlight this, the corresponding package, which is going to be down here, stroll Tiago Ros. In the package you create the machine directory, and this machine will be provided to you. So for example, we open it, you see here the initial state. It's important to see that this machine takes sensors from two parts. One is going to be a simulation of the total sensors, and the other one is going to be the actual switch to actually know what the robot is doing. So I invite you to explore the machine. I'm going to do a little change. This change is not changing the structure, but it's just to show you that if I do a change, I need to split. It's compiling it again. I need to copy the compile library and run an environment with the Tiago. I'm gonna run service converts the laser scan of the Tiago to something similar to the sonar sensors of the Toto. This wrapper I already demonstrated for you earlier in the video. At the moment the sensors see everything too far. We're gonna run the Ros switch, which I already also demonstrated for you, because our machine posed to the Ros switch. And at the moment this is posting stop. And now we're gonna run the machine in assumption -B to show you the states that it's changing. And it goes to several states to check the sonars at the front, and then it checks whether it has stopped, and if not, it pushes forward. We see some obstacle about 1.40 meters, in close to 80 centimeters, and very close to 30 centimeters, which is the danger zone. Area reports 29, 27, 26. In the behavior, move forward, tests, stop, and then it moves back. Because it's away from the danger zone, it moves forward again, stops, then it moves back, and so it's oscillating around the 30 centimeters. It gets inside 30 centimeters, stops, moves out of 30 centimeters.